This was used to build such famous structures as the Pantheon in Greece, which is more well known. Animal blood was used for some time in their earlier days for mixing concrete. Some details of history of civil engineering are bizarre, if not gruesome. But the art almost went into oblivion until the grand revival in the recent times, marked by the entry of Portland cement into the scene. With the progress of Portland cement concrete, it came to be used in bridges as substitute for stone initially. Concrete was first used for a bridge of 13.5 meter span across a canal in France in 1840. The Frenchman Lambeau, he built a boat 3.3 meters long. His famous rowboat, 3.3 meters long, made by, and this is again translation from French, made by plastering Roquefort cement on skeleton network of iron and wire. You will understand the sense, but it's an exact translation. This was followed by his English patent in 1885. You're welcome, but ladies, I am addressing you, you're welcome, but I don't like coming late. If you can't, then don't come. This is not a picnic. Coisin, another great man, and another Frenchman, took out a patent at about the same time on the structural use of reinforced concrete. Now, you will see how many people were interacting for the development of structural concrete. In 1855, Wilkinson, a Britisher, he secured in England a patent for concrete arch floor reinforced with tie bars. This is his exact words, which was discussed by no less than Fairbairn in his celebrated book in 1864. Then came Moynier. Moynier's first patent was taken 3 years later. It's all in the race for structural concrete. That's why I said a brief history of development of bridges and structural concrete. Now, just see, Wilkinson, then Fairbairn, then Moynier, and first Coisin. Then many others about this time took patents on reinforced concrete in one form or another in various lands. Thus, in the 19th century, which is 1800 somethings, reinforced concrete and consequently bridges were still in the empirical period of patents. The search for a basis of rational concrete structure design, not structural design, try and understand that, began in the last part of the 19th century itself. Thaddeus Hyatt is credited to be the first to establish a basis of analysis of stress in reinforced concrete. He made absolutely visionary statements that you take for granted today. He stated that the principle of bond, that the reinforcement must be able to resist sufficient tensile stresses to balance the compressive stresses in concrete, which you don't even think about now. But this was one of the fundamental groundbreaking statements of a visionary then. And then see what happened after that. Hyatt was an American lawyer. He was not an engineer. By education, he was a lawyer, but an inventor by nature, and was later to take patents on deformed bars, what we call tor steel in this country, I think. He published his, it is FE 500 now? Here? FE 500 now? Yeah. He published his 28-page book on the use of Portland cement concrete combined with iron in 1877, which may have antedated the design principles to emerge by good 2 decades. Then came another great man, Coisin, a German mastermind, a garment architect sitting in Berlin, was commissioned to what? This is from German, translation exact. He was commissioned to deduce the methods of computation of reinforced concrete sections, not analysis. This is pure design. And he published his design rules, design, not analysis, rules in 1886. Coisin. Coisin's idea on elastic design were printed 2 years later. Inelastic behavior theories for design of reinforced concrete or structural concrete sections, which were to be rejected rather irrationally later, appeared way back in 1898. We're talking of load factor design today. He did it in 1898, but that was unceremoniously rejected by those who thought they knew better. In 1909, the Joint Code of American Concrete Institute, American Society of Civil Engineers, and certain other professional bodies in the U.S. interested in reinforced concrete made its grand entry, the Joint Code. The French Commission on Reinforced Concrete had formulated its design rules way back in 1906. The visionary Abrams did again something which today we don't even think about, but that was a great masterly step then, and we are ever so thankful for that. Abrams, he gave us the well-known correlation of water-cement ratio with concrete strength, and he wrote way back in 1919, more than a century ago. Right? Almost 2 centuries now. That use only the smallest quantity of mixing water that will produce a plastic workable concrete. No effect, no problems now, no sweat. But it was not known. That's a big step in the history of development of structural concrete. And yet another historic pronouncement back then. With careful control of water and proportioning, attention was focused on workability, placement and compaction. Then came the wonderful Monsieur Freycinet, the Frenchman. We'll talk about him in a few minutes. He proposed back then compacting concrete by vibration, way back in 1917. A yet another historic development. And you know these vibrators that are used for mixing concrete? I'm sure you know. You know how many impulses per second? Think about it. And that he said in 1917. Just think about how many vibration impulses per second. And then came the improvement of composition and in fineness of grinding of cement. Finer the cement, the grinding is perfect. Then the smaller the particle size, higher the heat of hydration, better the strength. But controls had to be tight. This actually increased the strength, and this was a historic development in the business of structural concrete for high-strength structures, high-strength concrete structures. In Europe, they used mild steel like we used. Americans preferred it deformed, tall steel. The designers had chained themselves universally to a low permissible stress of 1250 kilograms per centimeter square, and the bogey of cracking and corrosion made higher strength and reinforcement almost a taboo. They wouldn't let you. Concrete and bridge engineering have come a long way since, at least in some ways. Precasting techniques using spine segments and even placing bearings at the bottom of the piers, not at the top of the piers, to cut the majority of moments because of the lever arm reduction. An early example, 700-meter pre-stressed concrete hammersmith, we did this in London then, is this. This is a spine box section with cantilever plates. And you can see I can't use it. This is a bogus thing. It doesn't work. I knew this wouldn't. It never works anywhere. You can see the bearings are at the bottom of the pier. So the vertical lever arm between the horizontal forces that are transmitted at the bearing level up down to the soffit of the foundation is a very small lever arm. Moments are cut out. But the construction is difficult to hold the pier against any toppling. That's why this is not a very popular method. And this is the blow-up of its segments of superstructure, and so everything is precast. Everything is precast. Then we had the other example, this is in Manchester, Mancunian Way flyover. Not precast, cast in situ, but here it is. Here it is. Then this is Al-Khalij Viaduct in Riyadh, Saudi Arabia. You have to see the bridges in Saudi, you will understand how good those bridges are. Not by Saudis, these have been done by outsiders. But this is 2 kilometers long, snaking like this, called Caterpillar Bridge. Now, there was no need for cantilever construction, the method by which this was built. You can see why the soffit of the bridge, the soffit of the superstructure is only 5.5 meters above the ground. Nobody, you have to be foolish to do this. But one of those sheikhs had gone to Europe, he saw a construction that looked like that, and he insisted, he said, I want a construction like this. We said, yes, why not? It was a laboratory exercise, we were paid very heavily, we did something we would never do, and that was this. And this bridge, how it looks at night, there is no pier. The superstructure literally sits directly on the bearings and the footings, because there was no need for it. There is no height. but we had to do it. But the beauty and the difficult thing about this is the cross-section of the superstructure, it's two parallel boxes going snaking around, is a hyperbolic paraboloid, longitudinally as well as transversely. No 5 square meters of shattering could repeat from one place to the other. You can imagine how costly this stupid exercise was. But he wanted it, so he got it. We got our money, he got his bridge. Flyovers have also been built totally using precast elements, a very quick one. And here's an abutment which is built out of precast elements. They are numbered 1, 2, 3, 4, 5, 6, 7. They're all organized here. If we had more time, because he has to go. These are the steps, and each individual precast piece, how it is built up like a mechano set. Precast abutments and wing walls. Then you can do a bridge like this. Everything is precast. You can see that. The pre-stressed concrete sheet pile abutments and wing walls, pre-stressed concrete piling pair, reinforced concrete abutments and wing walls, everything is that precast fully. You can see you can feel it, see it straight away.